My name is Sophie, and I want to tell you about the fascinating topic of contravariance. The motivation for writing this talk, honestly, are pretty humble. A few months ago, one of the junior developers in my team walked right up to me, and she asked me point blank, "Oh, by the way, like, what's contravariance? What's that thing? And like, can you give me a few examples of where you use it in practice?" And you know, like when your job titles includes words like lead developer or tech lead or something like that, you're supposed to pretend or maintain that sort of illusion that you know what you're talking about and you're somewhat competent in the language you're using. And I think that illusion came crashing down pretty quickly that day because I just couldn't give her a good explanation or example for that matter. And it was all the more frustrating because I felt I knew what contravariance was. I had, what I felt was a pretty good intuitive understanding of it. I'd used it in my code before, but when the time came to translate that intuition into words that another human being could understand, I completely blanked out. So the audience that I have in mind for this talk is twofold. One is those amongst you that are still perhaps fairly new to Scala, or at least new to languages that have the concept of contravariance, and just want to know what it is and understand when it's used. But then the other audience I have in mind is people a bit like myself. You may feel very comfortable with contravariance, but again, if someone puts you on the spot and you actually have to explain that, it may prove to be a little bit trickier than you'd like it to be. So hopefully, whichever of these two categories you fall into, you can get something useful out of that talk. I've structured it as follows. First, I want to go through an intuition building example, which is really a bit of a toy example, so it might feel a little bit tedious, but hopefully it's one that's easy enough to remember, because one of the goals I have here is I don't want to give you rules of thumbs to remember. I really want you to give you an example that allows you to work out from first principle, from pure logic, when should you use covariance and when should you use contravariance. So we'll go through that example. We'll cover both covariance and contravariance, and hopefully by the end of it, if you come out with anything from this talk, it'll be that example you can remember and refer back to when you're not sure which of the two to use. Then we'll look at a couple of examples of where contravariance is actually found in practice, outside of that toy example. And we'll end by asking ourselves, why is contravariance so confusing? I don't claim to have a definitive answer to that. But one thing I've noticed over the years is when you introduce someone to covariance, they seem to grasp it right away. But there's something about contravariance that makes it a little bit more sticky. People don't seem necessarily to get it the first time around. And I have a couple of hypotheses for why that is. Maybe some of you have more, so come find me after the talk if you want to chat more on this one. All right, but let's work through an example first. I have taken here the archetypal example of subtyping. So we have an animal, parent type, and it's extended by cats and dogs subtypes. You've probably seen this in dozens of blog posts already on subtyping, and you're probably tired of it already. But that's a good thing, because that example is probably etched somewhere in your brain, and it will take no effort for you to remember that. And then we'll look at a couple of type classes. We'll start looking at a rescue type class. So when you declare an instance of rescue for some type A, you'll be able to adopt an instance of A. All you need to provide is a name for it, and then you'll get an A back. And then the second type class we'll look at is a clinic type class, where you can bring in some patient of type A for an examination, and you get back some sort of examination report, some sort of statement about patient A, which will take the form of a string. So let's look at the first of these two. We can imagine defining an instance of rescue for the type dog. It's pretty straightforward. The constructor of dog takes just two values. It takes a name, which you're providing in the input to adopt, and then a breed. And here there's a few possible implementations you could think of. I think a sensible one is when we talk about rescues, you usually don't get to be too picky. So what I've done, I've just picked the breed at random for you here. That seemed like a pretty sensible implementation of this for me. You could also imagine defining an instance of rescue for our parent type animal. And in this case, I've added an extra layer of randomness because if you look at the signature, adopt here really returns you an animal. You've no way of knowing whether it's going to be a cat or a dog. So what I've ended up doing is just drawing at random. About half the time, you'll get a cat. About half the time, you'll get a dog. And again, that seems like a fairly sensible implementation. There might be other, but we'll go with this one for now. Right. So what I'd like us to do here is work through a couple of problem statements to try and really get a grasp of what covariance and contravariance are. So the first problem I'd like to work through is, let's say somewhere in my code I want to have the ability to adopt an animal. So I'm going to define a method that looks something like that. It's going to take a name, and then of course I'm going to need an instance of my rescue type class for the type animal. The implementation of that method should be super straightforward, looking at a signature. And yesterday I was doing a little bit of last-minute research. I needed a pet name, cliché pet name that would work for both cats and dogs. And I wanted one in Polish, so I ended up settling on, I'm probably butchering this, sorry in advance, but something that's like puszek, I think, which means fluffy. Hopefully it really is a valid pet name. It's not like insulting anyone's relatives or anything like that. But I've decided to go ahead with that one. So in my code, I'm going to declare a variable puszek, and that should be the result of the adoption process. But there's a slight issue. The issue being that in the area where I live, there are only dog rescues. There's no animal rescues. And the way something like this translates in my code is I needed an instance of rescue for the animal type, but all I've got is an instance of rescue for the dog type. So can I actually substitute an instance of rescue dog for instance of rescue animal? And how do I convince, if so, how do I convince the compiler that this is actually a sensible thing to do? So first, I usually like to just walk through a few logical steps. Before I try and convince the compiler to do anything, I just like to walk through the logic in my head and make sure that what I'm trying to do even makes sense to begin with. So we said I wanted to adopt an animal. We know that dog's a subtype of animal. And the question is, can I adopt an animal from a dog rescue? Now, if you pause and think about that for a second, an animal can be a cat, can be a dog. I'm not too picky. And a dog rescue will give me a dog. It's more specific than what I was asking for, really. But it still fits my requirement. So it seems sensible. I should be able to make the substitution that I've just described. So the answer to that is yes. Now, when you're trying to work out if you can substitute one thing for the other, usually substitution should work one way but not the other. So what I like to do is I like to flip the situation around and make sure that it doesn't work the other way around. So if I said I wanted to adopt a dog, which again is a type of animal, and I was trying to work out whether I could adopt a dog from an animal rescue. Now, if we think about that, and you remember the signature of the adopt method for the instance of rescue for animal from a few slides ago, the return type was just animal. There was no way of me knowing whether I'd get a cat or a dog. So it's pretty clear that in this case, the substitution would not work, right? Because there's a fair chance I would get a cat. I wouldn't be too happy with that. The cat probably wouldn't be too happy with that situation either. So the substitution works one way, but not the other. So how do we get this code to compile now? Because if I just do this, it's not going to compile, and the error I'm going to get is not particularly helpful either. I'm just going to be shouted at by the compiler and told, hey, I don't have an instance of rescue for animal. So the first thing I could do is I could try and force the compiler's hand and just shove the rescue instance for dog down its throat and hope that it accepts it. And again, the compiler is not happy with that, but it can be a little bit more helpful. This error message, by the way, is from the Scalar 2.13 compiler. You get also an error message in Scalar 2.3, obviously, but it's not as helpful. So I've picked the 2.13 compiler error message here. If you know how to get the same kind of detailed error message in Scalar 3, I'd be very keen to hear about that. I haven't figured out how to do that yet. But what I like about this error message is the compiler doesn't just tell me what's wrong, it also gives me a hint as to how I can fix my problem. It's like, okay, look, I found an instance of rescue dog, but what I need is an instance of rescue animal. So I can't compile this code, not going to work, but I noticed there is a relationship between dog and animal. And so I think there's a way around your problem, which is to add a little plus in front of your A-type parameter here, and we're going to see in a couple of seconds what that means, really. So we've worked out that what we're trying to do is sensible here. Now we need to convince the compiler that it actually makes sense. And really, there's only one way you convince the compiler that you can use one thing in place of another. It's to introduce a relation of subtyping between those two things. So whenever you have a relationship with a subtype on the one hand and a supertype on the other, whenever you need an instance of the supertype, you can substitute the subtype instead. And so for the same reason that whenever in your code you need an instance of animal, you can give an instance of dog instead. If you have this relationship of subtyping, you should be able to use an instance of rescue dog in place of an instance of rescue animal. And the way we create this relationship is adding the little plus here, as the compiler suggested, which is called making rescue covariant in A. So think of covariance as you take any relationship that exists within your type A, and you kind of lift that up into your type class. So you had a relationship here between dog and animal, and you've taken that relationship, you've lifted that up so that rescue dog becomes the subtype of rescue animal. And at this point onwards, the compiler should be happy with what we're trying to do. This code now compiles. In fact, I can even remove the explicit summoning. The compiler is clever enough now to figure out where to find a valid instance of rescue animal. In this case, going to use the rescue dog. So that's all good. So that was covariance. That was the easier one of the two. Now let's look at the second example. We have a clinic type class. So we said again, we can bring a patient of type A, get some sort of examination report back. Again, we can walk through a couple of implementations of this type class. One for the type dog could look something the following. There's not much to say about a dog, but you could print its name and its breed, something like that. We could also have an implementation for animal type. And in this case, I might want to use pattern matching, knowing that animal can be one of multiple things. So I might want to have slightly different behavior based on whether I've got a cat or a dog, something like that. So let's walk through a second problem statement together. Let's say I want to take my dog for a checkup. So I'm going to define a method that looks like this. Takes a dog, takes an instance of clinic for dog, and should return me an examination report in the form of a string. Given the signature, the implementation is incredibly straightforward. And here I went with the cliché French name for dog, which is Médor. So we have a dog called Médor. It's a Labrador. And we want to try and obtain an examination report for Médor. Problem though, there are only animal clinics in my area, which in code we translate to something like this. So we just saw that my method requires an instance of clinic for the type dog, but all I've got is an instance of clinic for the type animal. And now we need to work out, first of all, does this even make sense? Can I do this sort of substitution? And if I can, how do I convince the compiler that this is sensible? So I want to take my dog for a checkup. Dog's a subtype of animal again. Can I take a dog to an animal clinic? And if we think about it and look back at the implementations a few slides ago of clinic for the type animal, we saw that it was capable of handling a dog. Yeah, it does more than what we need. It's also capable of dealing with cats. But again, it fits the bill. I think it's fine to pass something that is more powerful than what you need, as long as it does what you need. It's fine that it does also more than that. So it seems that this should be sensible. This should work. Again, I like to go through the exercise of trying to do this the other way around. So for the sake of the argument, let's say I've got two animals. I've got a cat and a dog, both of which are subtype of animal. Could I take them to a dog clinic? And the answer here is obviously no, they wouldn't know what to do with the cat. So again, to make sure you're doing substitution the right way, it usually helps if you flip the situation around and make sure it doesn't work the other way around. So how do we get this code to compile? Because at first, it doesn't, and you get the rather unhelpful message that the compiler hasn't found an instance of clinic for dog. So again, you can try and force the hand of the compiler a little bit, giving it the instance of clinic for animal. And you will get a slightly more helpful error message telling you, well, can't compile this, but I noticed there's a relationship between dog and animal, and I think if you add this little minus sign in front of your A type parameter, that might fix your problem. So what is this minus sign from a type parameter? What are we trying to do here concretely to convince the compiler that we can do this sort of substitution? Well, we're trying to convince the compiler of the following. Right? If we want to give an instance of clinic animal in place of an instance of clinic dog, then we need to introduce the following subtyping relation. So we need to somehow make clinic animal a subtype of clinic dog, which is exactly what contravariance would do. When you add this little minus sign here, that is exactly what it does. We make clinic contravariant in A, which means that whatever relationship exists within the type A is now lifted into the type class, but it's also flipped around. So whereas in the relationship between dog and animal, dog is on the left-hand side, is a subtype. Now that clinic has been made contravariant, it's clinic of animal that becomes the subtype of clinic for dog. So we've switched things around. But this will now allow us to use an instance of clinic animal in place of an instance of clinic of dog, as we said would make sense. So that was contravariance. That's all it is, really. Nothing more than that. So where do you actually find it in practice? Because this was more of a toy example. I don't imagine many of us work with that time of domain model day to day. So there's a few places. Number one is probably codex. So I've taken these two type classes pretty much straight out of the CIRC library. I've just added the JSON name in front of the type class name to make it explicit. But you have a decoder that can decode some JSON into perhaps an instance of A, or perhaps returns a decode error. And you have an encoder, which does the opposite, encodes instances of A into some JSON. And usually, when you work with codecs, you'll find out that the decoder is covariant. I'll let you work out if you want why that's sensible. But the encoder, on the other hand, tends to be contravariant. And we can convince ourselves of that looking at a quick example. If you had methods like this, it tries to encode instances of dogs into JSON, which take a dog and an encoder, and a JSON encoder, sorry, for dog. The following would compile, obviously, because we're giving it exactly what it expects. But the following would also compile. Because again, we're doing the same thing as with Animal Clinic. If we pass a JSON encoder of animal to our method, we're giving the method something that does what it requires and some more. But it's acceptable to give it something that's a bit more powerful than what we strictly required. So that compiles again. So yeah, whenever you encounter codecs, remember decoders will tend to be covariant, encoders will tend to be contravariant. The second place you might encounter it is functions. If you ever taken a peek behind the curtain and had a look at what a function really is in Scala, you'll notice they are traits. There's various traits depending on the function arity. So this was for a function that takes a single argument, one for a function that takes two arguments, and so on and so forth. And you'll notice that all the input type parameters are contravariant, and the output type parameters are covariant in functions. And what this allows you to do is something like this. You can define a function that works on a wider range of inputs. In this case, it works on any animal and returns you a string. And you can assign that function to a val that works on a smaller set of inputs. You can assign that to a function that says I'm a function that only works on dog, and return a string. And the reason you can do something like that is thanks to contravariance, thanks to the subtyping relation you have right there. With the output being covariant, you can do the other thing as well. It's not as interesting, but yeah, you can also have a function that returns a more specific kind of output here, a function that only returns dogs, and you can assign that to a val that has a wider range of outputs. The reason you can do that is thanks to covariance. So by this point, you may have started to see a pattern here. These are the examples that we looked at where we encountered covariance. And if you look closely, you'll notice that the A type parameter here, the covariant type parameter, tends to always be used in the output. And inversely, when we looked at contravariance, we looked at type classes where the type parameter tends to be used as an input. So that's the typical situation where you encounter covariance, contravariance. You'll tend to encounter covariant type parameters when they use it as output, contravariant type parameter when they use as input. So you can remember it as a rule of thumb if you want. I prefer not to. I always prefer to work it out from first principle when I have a doubt, rather than resort to that. But yeah, that's a good rule of thumb if you want to remember it as well. So why is contravariance so confusing? What's so special about it? Because we saw it seems pretty straightforward. I have a couple of hypotheses here, but yeah, if you have more ideas, very curious to hear them. The first one is it's far less common than covariance. You encounter covariance very early in your Scala journey. As soon as you start looking at collections or error types, anything that's like an option in either a try, you'll come across covariance pretty quickly. Whereas contravariance, not as widespread, right? Until you start looking at how functions really work or codecs or things like this, you may well spend a few years writing Scala without ever needing to really understand contravariance. So that's one reason, probably why it's more confusing. But the second one is I suspect that sometimes people attribute to covariance behavior that really is provided by subtyping. And you can't do the same with contravariance. And I think that might be one of the sources of confusions. I caught myself, in fact, doing that a few weeks ago while working on this talk. So if we take an example like the following one, we take a function with arity 0. It's a function that always returns you the same thing, and it's covariant in R. Now, the following works thanks to subtyping. So I can create a new instance of func for animal, whose apply method should always return an animal and return a dog instead. Now that works because of subtyping. That works because dog is a subtype of animal. The following, however, works thanks to covariance. The only difference between these two pieces of code is these two type parameters here, right? Otherwise, they're absolutely identical in every other way. But the second example works thanks to covariance. I am able to assign to a val that is type func of animal, I'm able to assign to it something that is typed as func dog. And I can only do that thanks to covariance. If I actually removed covariance from my type class definition, this would stop compiling. And so you can see how close, when you look at code, and this is a very simple piece of code, when you look at more complex pieces of code, you can see how similar the two might look. And what I tend to see sometimes is people try to do this with contravariance. They're like, okay, well, let's make the func type class contravariant now, and let's try and do something like that. I'm going to declare, I'm going to try to create an instance of func for dog, and I'm going to have apply, which is supposed to return instance of dog, instead return an animal. And of course, that is never going to work, right? Like you just can't do this. Subtyping won't allow you to do this. But I think some people jump to that conclusion and try and do something like that, expecting covariance to allow them to do this. And then they get confused when the compiler just refuses to make this work. At least I've caught myself doing that a few times. So I think that's one of the sources of confusion. Right. So quick recap. We started with invariance. So invariance is, you don't have any plus or minus in front of your type parameters. And what invariance means really is whatever relationship exists within your type A is never propagated into the type class. There's no relationship whatsoever in this case here between the JSON decoder for dog and animal, regardless of what relationship exists within dog and animal. Covariance, you add the little plus sign in front of your type parameter, and covariance just take whatever relationship exists within A, lifts that right into your type class. And it tends to be used for output type parameters. So you'll encounter it in decoders or in function outputs. Contravariance, on the other end, you add a minus sign, and contravariance is you take any relationship that exists within A, you lift that into the type class, but now you flip it around. So in this example with the JSON encoder, we have made the JSON encoder of animal the subtype of JSON encoder for dog. And this works because it's fine to provide type classes that do more than what you require. It's fine to provide in your code something that's more powerful than what your code strictly needs. That's the reason contravariance works. And it tends to be used for input type parameters. You'll find it in encoders or function inputs. Right, thank you very much. That was it. I see we have a few minutes left for questions. I don't know if there are any.